Welcome to this NPTEL lecture on principles and techniques of modern radar system. We have discussed in previous lectures, we have seen the tracking radar. Now, today we will start our discussion with target detection. Basically, the detection theory we will see, and to start with this discussion, I refer you to the previous block diagram of pulse radar or pulse Doppler radar. So, this was the block diagram of pulse radar. The same thing was there in the pulse radar. So, there you see that the received signal after the antenna receives it. So, we get it here you see the antenna. So, through duplexer it is coming and it is put to mixer. So, RF mixer mixes that and makes the IF signal. Now, this IF amplifier we used to say, today we will see that what is the IF amplifier implementation. Actually, radar people call this match filter. So, we will start our discussion from that what this IF amplifier is. So, we can say that when the received radar echo signal is put to RF mixer, we get IF signal. This IF signal is basically fed to a match filter. Today, we will discuss this match filter. Most of this thing may be known to you from your communication classes, but actually this match filter was invented by radar people, because for radar the echo signal that is much weaker compared to the communication signal that goes to the receiver, because it is a two-way journey for radar, where there is communication, it is a simple one way from transmitter to receiver journey. So, that is why we know that the signal in the open space that its power gets reduced by 1 by r square inversely to the square of the thing, and for radar we have seen that actually that target's distance, if the range of the target is r, then the signal that is received, that power is proportional to 1 by r 4. So, that means it is a very weak signal. So, that is why radar people, early radar researchers who were designing that radar receiver, they were bothered with the question that how to detect such a weak signal. So, what is the best possible IF amplifier that we can design, and in that process they find out that match filter is the optimum. It is the best possible IF filter, because it maximizes the SNR. There cannot be any filter better than that. So, we will start that discussion today, the matched filter. What is a match filter? And so, it's we will first see the theory of match filter, then we will see that how this match filter not only maximizes SNR, it also helps for detection. So, it actually from this analysis we will also get the clue that how we can make the detection very reliable, and also what is the best possible, how we can improve the resolution of this detection thing, range resolution. So, all those things will come from this analysis. So, I will start this discussion of match filter. So, let us say this is the match filter. And so, we know that in electronics, if there is a black box, we can characterize that. For LTI systems, we can characterize it either in the time domain. If we characterize that, it is called its impulse response HT. In frequency domain, if we do the same thing, it is the transfer function H f. So, let us say the match filter, our match filter is this characterized in time domain by H t or in frequency domain by H f. We will find out what is the value of this H t or H f. Okay. So, what is the input to the match filter? As I said that the mixer output. So, that is here we are assuming that the thing is, let us say, actually there are signal and noise both are there, because the transmitted pulse that has gone through the free space to the target and from target again it came back. So, in the process it got corrupted by noise. So, what we get is the this we generally assume in our models that noise is additive. So, with signal it gets added, but for analysis actually we do it separately, because the signal and noise, their characteristics are different. Signal is a deterministic signal. So, it has a functional representation, whereas noise does not have, noise is a random signal. So, it does not have that characterization. Also in communication you have seen that various random processes from which a random signal get created. So, actually from that random signal I should not say that I can represent noise by any function, but what we can say that at any instant I am receiving a noise. Let us at our in time instant, let us call that value, but obviously any random signal at particular time has a value. I cannot know what value it will take. Also for signal I do not know what value it will take, but I can describe that either by a function or by a table. For noise I cannot do, but if I say that this is n t is not the function representing noise, but it is the sample value at that point in at time t. So, in that sense we write that, but obviously this noise signal, deterministic signal, that has a we can define power etcetera for that. For noise type of random signals we cannot define power, but we know that from if we know various sample values, from that we can find the correlation function, and from that there is a Wiener-Khinchin theorem by which we can find its power spectral density. So, we will treat them differently in the analysis, but let us say that in the input I have the signal part of the received thing as if I can separate, but in reality I cannot separate. This is for analysis, this is the abstraction, that signal part is x t and it is n t. But here I want to say that actually I am assuming that x t is the signal part that was transmitted by the radar transmitter. I know that what signal got transmitted. For pulse radar we know it is a RF carrier signal, but its envelope, amplitude envelope is something like pulse, whatever. So, transmitted waveform I can say. And so, I am getting the received signal that I am assuming will be delayed. So, I will have to put that delay. So, it will be, let us say, the round trip delay. What is T 0? T 0 is the round trip delay, round trip delay. So, the signal I am getting is x t minus t naught, and here I am assuming that the amplitude is same, but in actual reality that is not same. Definitely due to this there are, we have seen heavy loss in the just in the signal transmission also, the path loss is there etcetera. So, the amplitude part is will be definitely a. So, this x t and this x t minus t naught, they are different in amplitude, but now I am not going into that details. When we will take these two together, that time we will take care of that. So, I said that I have received the signal part as this and added with this sample value at that time, when the match filter will see this thing, that is NT, let us say. So, this, or I will more specifically call this is the output, input. So, NIT, this is the sample value of the input noise part that is coming. So, actually the input to the match filter is this signal part plus the noise part. Okay. And this x t minus t naught. So, this is an analytic signal, deterministic signal, and this is a sample value of the noise that I am calling sample function, and I am writing like this. So, at the output, due to this I will get a signal part will be changed to x output O t, and the noise part after passing through this match filter, that will generate a noise like N naught t. So, this is my picture. So, we will now find out what is the expression for this H t or H f. Anyone, if I do, we know Fourier transform. So, we can do that. So, I can say that what is the input signal at x I t. So, that means these two together I will call x I t, that is actually x t minus t naught plus n I t. Now, so and this output, so this is x t is the input, and these two again together will actually will be a sum. So, I am calling it y t. So, that is the output of the match filter y t. So, y t is x naught. So, this will be also delayed because x t is given. So, I should write that also as t minus t naught. So, it is t minus t naught plus the sample value of n that I am calling n naught t. So, now you see that I know one thing, if the impulse response is h t of the match filter. So, from our electronics circuit knowledge, I can say that what is the output, this x naught t minus t naught, that is nothing but x t minus t naught convolved with h t, and also if I take that liberty that sample values will be also definitely this correlation thing. So, this is I can say n I t convolved with h t. So, let me name the equations because some mathematical derivations will come. So, let us make this first one, let me call equation number 1, and this one let us say equation number 2. You see, I am not writing this because actually in the strict functional sense I cannot write this to this n naught t is equal to this. Actually, this does not have any meaning, just I am writing that to show that okay, something noise values. So, if I take those values and do the convolution, I will get the output thing. Okay. So, that now what is my this one let me call 2 and this one let me call 3. So, this is my 4. Now, I can take the Fourier transform of equation 3. So, Fourier transform of 3. So, what I get? I know that I will get an x O f, and that will be Fourier transform of that. So, let us say that we say this the Fourier transform of, or here I will write, sorry, so if I take Fourier transform, I will get x naught f, and that will be nothing but x f e to the power minus j 2 pi f t naught, then h f. H t has Fourier transform h f. What is x f? X f is the Fourier transform. So, the sorry x t, if I take Fourier transform, I get x f. Generally, this thing we follow that this x is capital, this is a, because their functional relationship is different. This x and x, so that is why we make capital, that it is a different function, that you know. So, x t x f, h t h f I have already said. So, I can write this. Let me call this equation as 5. That means, we know that if I have a delay, so in the Fourier transform domain, this goes like this. So, now I can find out that what is the total signal power here, because ultimately we are bothered about the, after match filter we will find the SNR. So, SNR means signal power divided by noise power. So, at the output we are bothered with that. So, what is the total output signal power? Total total output signal power. Now, we know that there is a theorem called Parseval's theorem, by which we know that if we know the Fourier transform, that means, if I know x f, from x f also I can find the power. So, total output signal power at t is equal to t 0. So, that by this I think all of you are familiar. So, that will be nothing but this minus infinity to plus infinity x f square d f. Or to be more precise, I should not say this, let us say this square. So, that is, if I put the what I got from equation 5, then this is x f h f e to the power minus j 2 pi f t 0 d f d f, then whole this thing and then square. So, this I know, and let me call this equation as equation number 6. Okay. Now, I am interested about the SNR at the output. So, I will also find what is the output noise power. That noise power I can write that output, because noise we can define power through the power spectral density. We know the power spectral density. So, in the frequency domain we can integrate and find out that output noise power, that if I call N naught, then it is minus infinity to infinity N I F then it has passed through the match filter. So, I will write H f square d f, where what is N I f? N I f is the, I can say, input noise power spectral density. This is an analytic thing and I am writing this. Please note that this input noise PSD, I am not assuming any characteristic of this noise, that whether it is white, whether it is Gaussian, all those things. It is a general input noise PSD that can be always found, because you take the various samples of noise, either you can take ensemble things, that means spatial samples or time samples, and there are various properties of noise by which we can say that we can find the correlation between them. Then we can find the Fourier transform of that, and that is the noise power spectral density. So, NIF, if it is there, then I can write this. Now, again name this equation, that this relation between the output noise power and input noise power spectral density, that will then come as my equation 7. So, now I am in a position to find the output means match filter output SNR at t is equal to T0. So, I will call it SNR T minus T0, that will be the signal power. The signal power was equation 6 by equation 7. So, I can write that minus infinity to infinity x f h f e to the power minus j 2 pi f t 0 d f, then I will take the square divided by this, that is minus infinity to infinity n I f h f square d f, then this. So, this is the SNR. So, this equation let me call equation number 8. Okay. So, now I recall that what is the maximum value of that, etcetera, that actually this is this the, you can see that we know Fourier transform, etcetera, those are complex quantities. So, H f is complex, X f is complex, e to the power minus j, that is also complex, N I f is complex, H f square, that is real. So, now the question, this is real, but this N I f is complex. So, it is a one complex thing by one complex thing. So, that thing also their form is square. So, that is, mathematicians have solved this problem, that what is the maximum upper bound or what is the upper bound for this thing. So, that is called Schwarz inequality. Schwarz inequality. So, we will take the help of that. What is the Schwarz inequality? Schwarz says that minus infinity to infinity. If you have two complex function, one is x1f and another is x2f, and if you have something like this, that their product, integral of their product square divided by 1 of that square df. That means, product of two complex functions, their integral, then this over the whole range of f, and then that integral square divided by the some another integral, infinite integral. So, if you have that, then you have the upper bound given by this, that upper bound is minus. So, this ratio always is has an upper bound, that is x 2 f square df. This is called Schwarz inequality, and he also said that this upper bound gets achieved. So, the equality or upper bound, because always this ratio is less than the right hand side. So, equality holds when the x 1 and x 2 they are related by a constant. So, equality holds when x 1 f is some constant k into x 2 f with a conjugate. So, this is a thing. So, here I will say that this is a arbitrary constant. So, that means, when these two complex functions, so they are related like this, then you get that this ratio is equal to this, and that is the maximum value. So, we will have to apply this Schwarz inequality in our case. So, what we do? We now make that we will have to, from our that relation 8 SNR relation, we can choose judiciously this x 1 f and x 2 f. So, x 1 f if I choose like this, you see that n I f root and outside h f, and x 2 f if I choose as x f e to the power minus j 2 pi f t naught by root over n I f. So, if we have this choice, then we know that maximum value of this. So, then you can see that if we look at equation 8, you see that the actually integral. So, this where is SNR, this equation, and you see that this expression is nothing but same as this LHS of the Schwarz inequality, if we choose x 1 2 and x 2 f in that manner. So, now we know that maximum value of this SNR will be what. So, we can say that SNR is maximum when root over n I f h f is equal to some constant k into x star f e to the power j 2 pi f t naught divided by root over n I f. You see, this is a real number, that is why we can take this. So, okay. And this is the maximum, and what from this you see we are getting the famous relation that H f gets determined. So, what is H f? It is our match filter transfer function, but it is H f is equal to k x star f e to the power j 2 pi f t 0, that means some phase, then divided by, sorry, that won't be, I think, square root, that will be n I f. So, this is a very very important thing, and I can now give an equation number to it. It is equation 9. Also, I am making this highlighted that this will be used. So, we were looking for what is the filter that can maximize SNR. So, this is the filter that can maximize SNR on, because I know what is the what signal I transmitted, I know. So, I can find out what is the x star f. Also, I know, if I know what is the delay, then I can find this, and the if I know the noise input noise to the match filter, I know the power spectral density for that NIF, then I can find only Kn to be chosen. So, this is an important relation, and we have, this is the actually basis of match filter, and once I have HF I can find HT, etc. So, this actually was our goal. So, we have got that goal, that match filter we could find, and an expression for match filter in terms of the noise, input noise coming to the filter, and also in terms of the signal. So, that is a remarkable achievement, and we will discuss more on this match filter in the next class. Thank you.